Thank you, Spencer, my friend. I'm so scared of you guys, I can't even offend you anymore. Um, Even if I want to, huh? Okay, so the rest of them, guys, and I promise we will talk about these in detail, especially the lighting system. So this chapter talks about how to read how many receptacles in each circuits and the label and so forth. And I have no doubt that all of you guys are very comfortable with reading the the lighting system and the receptacles and the symbols for this project. Let me go and highlight a few things though. If you guys look in page 28 and 29 and actually 27, they go through identifying each one of these symbols from a panel into a light and the symbols that they use and so forth. So please, we have a symbol list that we use, Spencer, for all our projects. We know how to identify them. Floor, receptacles, different type of receptacles, different type of switches. The good news for us guys, especially with Revit right now, we have loaded yesterday, Spencer, we loaded all the mechanical equipment and we loaded all the lighting, and so these are probably redundancy as you do. I want to bring in page 29 something probably in Revit. I don't know how it's going to be showing it. It seems Revit showed the conduits as a green, right? Well, I was looking at you. It's just the connection that shows it as a green. If we're showing it in 2D in page 29, the upper right, guys, you can see if the circuit is like a circle with a dot. Please be aware that if it's a dot, this means the conduit is going what? Up, going up. If it's a cross, if you're showing conduit, the conduit is going down, up and down. That's something probably we need to know. The rest of them, I'm very confident that you guys have no doubt that you know how to read these. So that's what that. Talk about the neutral conductor, neutral point, and ungrounded. I hope by now, guys, that you see there's 3 conductors you must know in any branch circuit or feeder, right? Every branch circuit. You have to know that the neutral conductor, right? You have to know the neutral point that generates the neutral conductor and the ground. Very simple. In a 3-phase system, here's what we're talking about. Here's my neutral. This is my neutral. This is phase A. This is phase B. This is phase C. So, Mr. Irbab, phase A, B, and C, that will be the ungrounded conductor. A, B, and C, right? Everybody knows that? That's the ungrounded conductor. Ungrounded, the hot. I hate it when they define bread, everything with ground. In the code, they define everything by ground. Ungrounded, grounded, grounding, and so forth. And the neutral conductor or the grounded conductor, which is basically the neutral, right? And here, the only thing that they're missing here, and I'm going to put it in this is my transformer. The only thing that they're missing, guys, is the grounding conductor, equipment grounding conductor. So this is my equipment grounding conductor. So basically, these are all the type of the conductors that we use in a feeder or branch circuit. I hope by now, guys, that you are with us in a second, that you know at least these 3 types of conductors: grounding conductor, grounded conductor, and ungrounded conductor. Everybody knows that? Ungrounded conductor are the phases. Grounded conductor is the neutral conductor, and the grounding conductor, for the most part, when we talk about branch circuits, it's always the equivalent grounding conductor. Any questions about these? Very important when we do branch circuits. So as you pull your branch circuits, Spencer, you're going to be asking yourself, if it's a single phase branch circuit, I need my neutral and I need my hot. What else with it? And a ground. And a lot of us know that, guys, if you're using conduit like these one, the shell of the conduit itself will act as your equivalent grounding conductor. So if I'm to feed this receptacle, or 3-phase receptacle, I think this is a different one. Say if you are going to be using this, feeding this receptacle from an EMT, all what you need to bring to it is 2 conductors, hot and neutral, and the ground will go through what? The shell of the conduit. So that's very important to know the advantage of using EMTs in commercial building. EMTs it will drop, if you're using conduit, it will drop this conductor for you. Very good advantage, right? No more copper. You don't need to pull another conductor with it. You can if you want to, but you don't need to. And it will save you money. And if you ask me, it will be, even from an engineering point of view, it's counterproductive to pull a grounding conductor in EMT. Unless you have like 500 runs of EMT, then that's a whole different story. Any question, guys, about these? This is really, that's the slide I want to emphasize, is the definition of grounded, ungrounded, and grounding. Any question? Everybody knows that one? And the rest of this chapter, guys, talk about how they did the wiring. In the drugstore, they did the low voltage remote control system in it. In our project, the funny thing is, in the project that you guys have, we will have a low voltage control system, and I promise you we'll talk more about the low voltage. We basically want to have we're going to have relays, and all the lights in the commercial building, we're going to bring it from. Let me just draw a circuit, and how do you do a low voltage control system? So here's my 20 amp circuit coming from here. This is my 20 amp circuit. This is my conductor number 12. Okay, I'm just showing the phases. Number 12, and grab it from here, from right in here. We land it in a contact, and we take it all the way to my light. This is the phase, and the neutral came down from here and terminate here, come back, and go all the way to the neutral side. So this will be my phase A, and this will be my neutral. So that's basically how you control a light through a relay. This is just showing the power part of it. Let me show you the rest of the story. This is not just the rest of the story. The rest of the story, this is, guys, the power. This light is, let's just say this is 100 volt amp light, and fed. I'm just showing one. It could be multiple of them. In reality, it would be another light over here, and you can tab from this side and tab from this side and feed another light. You have two lights now fed from a 20 amp circuit and controlled by a contactor, a relay. Okay? Let me show you what they do inside this relay. Right? This is my relay. Relay or contactor. Lighting contactor. Relay or lighting contactor. So it's a device, relay or lighting contactor. What they do, guys, this is the power circuit. They call the power circuit. There's a control circuit. The control circuit, Spencer, they come with the relay has a coil. Did you guys wire relays with Gary? With us? The relay is a big fat name for two things. It's a contactor that opens and closes, and a relay that physically, mechanically drives this contactor by magnetic force to close and open it. So here's the contactor. You land the hot in one side and you pull it from the other side. That's a contactor. The relay, the coil, is a 24 volt coil. This is a 24 volt coil. And you bring this guy to, in our case, to a lighting control panel. And you power it from a lighting control panel. And you put, you bring it to a lighting control panel, and you put a tiny little switch in it here, and you bring two conductors to a lighting control panel relay. So here's your low voltage switch, guys, and I'm just simplifying it, really simplifying it. This will be also fed from a 20 amp, 120 power lighting control panel, and then when you close the switch, there is a transformer. Some of you will say, where did you, Chad, get the 24? There's the power come over here, and a transformer, 24 volt. You close the switch, you energize the 24 volt coil. When you energize the coil, it pushes these contacts to close, and then the light will go on. And that switch, guys, looks exactly like this switch, except it's a low voltage switch. Low voltage switch. Literally, low voltage. You bring, what does a low voltage switch mean? You're bringing 24 volt to it. What's the advantage of this? Mr. View, you don't need an electrician, licensed electrician to install it. Cheaper.
You need to do everything else.
Huh?
You need to do everything.
Yeah, you need it to do, but if you have a lot, And really, that's what they say the advantage is. But really, the main advantage of it is not saving money. You can't save money. The main advantage of it is if I set this, this is just simplified, guys. I can send another circuit to the coil, and I can push a button in my laptop from China, send the signal through. This will be an internet connection to this panel. I'm sitting at China through the internet, send the message to my laptop, goes to the brain of the lighting control panel. This is an electronic piece of equipment, has a brain in it, and then energizes this coil directly. It will override. You can design it to override that switch and turn this light on and off from anywhere in the world. If I were to turn all the light on and off, guys, are done with it. I can turn them off, on, off, half of them on, half of them off. Timer. You can put them in a timer and so forth. But that's basically what they're using in the drugstore. They're using low voltage to give you better control, energy efficiency, Brad. With energy efficiency right now, using occupancy sensors and using low voltage control and light sweeping at night, turning all the light off. All this good stuff would be happening in a lighting control system. Any question again? Yes, sir.
They have a system like that in where I work in the upstairs, but I think it's like the first one that was ever put in. It's really old.
An awkward.
There's a control box like over by the panel, and it's kind of funny because all the wires going down the switches are just low voltage, like a phone wire circuit.
Yeah. And, number 16 and number 18.
And then they run their three-ways off it too, from one side to the other. The problem being is that the fixtures in that particular area are old ballast with T12 8-footers, and so when you turn the switch on, the toggle switch, when you walk in the room, the control panel just goes chum.
Yeah,
it's like
the contactor.
And all of a sudden there's just buzzing everywhere.
Yeah.
It's just because it's so
Yeah.
ancient, but it doesn't really do. I don't really understand why they would have put it in there if it was just an experimental thing, but it doesn't do anything for their application. They have no like timer on it where at 8 o'clock at night it automatically shut off.
Yeah.
It doesn't really make any sense for it. It's actually a lot more work for me to try and redo it,
And
just to make it,
the idea, guys, of a lighting control panel is give you a huge amount of control over your lighting system for energy saving and for control. For control, you can sweep the light, turn them on and off. I know there's so many systems. We are bringing a lighting control guy. He's going to be coming and he will tell you more than you need to know about. And he has a demo which you can play, push the buttons. And by the way, these switches could be a snap switch like this or push button switches. You push a button, energize the coil. I can't emphasize, Spencer, if you hear the word low voltage control, lighting control system, always remember they have a coil. You energize the coil to close the contact to turn the light on. Really, yes. How do you energize the coil? You can energize the coil by putting a snap switch, right? And you wire it by number 16 or 18. These are 24 volt guys system. So snap a switch wire with number 16, turn, and here's the power here. You turn it, you energize this coil, it shuts, or you can grab the whole wiring in here, and you have a contact controlled by another relay here that receive a signal from China through the internet, close an electronic contact, guys, here, energize this coil to turn the light on and off.
I guess
Or a timer, or yes, sir.
Well, I guess I was always under the you wouldn't want a snap switch on that. I mean, the whole purpose of having a lighting control panel is so that it's automatic.
Absolutely. You can have override though. You can override these.
Sure.
You can override them. There's so many ways, and I really don't want to do the best lighting design, at least from my point of view, guys, is not where you see that coil here, Brad. I put the coil and the contact separate from the panel. Most likely, the good design will you grab the whole deal here and you put it right inside the panel. So now your coil and contact churs and all the coils are right in the panel. You have full, complete control over the coils, and then you bring your switches. See that what really the good stuff is. You bring the wires. Here's my switch, for example, and my switches is going also to the panel, and my coils is going to the panel. So I can turn the switch here, control the coil that's inside the panel to turn this on, to turn the light on and off, and then at the same time here inside the panel, you can override the signal that's coming from this switch. Long story short, if the switch is off, you can override it by another contactor and turn it on and off. They use it for emergency light. If you need this piece of light, guys, as an emergency light, and it's a low voltage system, you can use it as emergency light. Now, you have a low voltage switch here. You turn it off. Now I turn this light off. What happens if I have an emergency? I lost the power in this area. There is a switch here. It will be programmed. If you lose the circuit coming to this area, it will override that switch that I just turned, and it will turn that particular circuit on, or that particular fixture on. So there's so many ways of programming, guys.
Does it have its own transformer in it?
Yes, you have to transform it into a 24 volt. Yep.
And on that other switch?
This
The
gun?
emergency one? The emergency one have its own transformer to work that switch?
No, everything is powered by one transformer.
Oh, right in there? Oh.
Right in here. This transformer, guys, is just bringing the 120, knocking it down to 24 volts so you can power the relays and send hot to the switches.
So
Just
that's
knocking the voltage down.
Just a time off delay or something like that?
Time off delay, time on delay, depending what you want to achieve. Absolutely. So, but that's kind of what they're doing in the drugstore. They're adding this type of lighting system. And the others, guys, the other places they're using regular lighting systems. So that's basically what I want to emphasize on that particular one. Any questions about this? So please, really is reviewing just a simple list here that we have on this particular chapter. So do me a favor, read it. The neutral grounding is the most important ones, and the lighting, low voltage lighting control system. Basically, the rest of them are high voltage control system, which is basically bring a 120 here and you take it all the way to light, turn it on and off. Any question, my friends? Any question about that one, Mr. Bab? Did I put you to sleep yet? And I want to emphasize the stuff that's really need emphasizing, guys, and I don't want to, oops, there's that one. Not to minimize anything. Chapter 3, guys, talk about load calculation, and I'm not going to torture you with another load calculation. I just want to, let me see here. So when we did the load calculation, guys, and again, I gave you a sheet. Everybody has that sheet. A couple of things, guys, I'm just going to summarize the light calculation load. When you do light calculation, the first thing, Brad, you do is lighting calculation. You will need to find how much volt amp you need for that particular commercial building. Two ways we calculate this, if you guys remember. We did it the actual load when we know it, and we did it based on table 220. Table 220, we went and find the volt amp multiplied by the square foot of the building. That's the chunk for the light. The other chunk, if you guys remember, that we did is Volt-Ampere Receptacles. Every single receptacle in the building, we're going to assume is going to have 180 volt amp. So, piece of cake, multiply them all by 180, add them all up, and then derate them. The first 10,000 at 100%, anything higher than 10,000 at what? Anybody remember when we did the load calc? The first 10 at 100%, anything higher than 10, cut it by half, 50%. So that's how you derate them. If you don't know the receptacle load for only a commercial building, what's the assumption? If you don't know the receptacles yet that you're going to be installing in a commercial building, the code allows you to give, if you guys remember that, 1 volt amp per square foot for the building, just to start. So receptacles, lights, and then the rest of them, guys, are a piece of cake. Then you're going to look at your mechanical equipment, add your mechanical equipment. Take the largest, multiply by 1.25, and add the full load current of all the other mechanical equipment. If it's heating, cooling, Ryan, what do you do with heating, cooling? You're going to pick the largest, heating or cooling. And then you're going to keep adding it. Sign, if you have your commercial building, you need a sign. You assign I think, remember, 120 volt amp for every sign. Multi-outlet assembly, if you have multi-outlet assembly, you have assigned the load for the multi-outlet assembly if it's continuous. 180 for every 1 foot. If it's non-continuous, 180 for every 5 feet, if I remember right. So this chapter, guys, just to review exactly what we did for the whole calculation. So please read it. Do me one little favor. I think we did the sheet that I gave you. Honestly, I think it goes in more details than this chapter. It's multiplying the square foot of the building and so forth. Here's one thing I didn't do my sheet, and they're doing it, guys. They're taking the storage area. If you go to table 220.12, the storage area, and you find the Volt-Ampere storage area is 0.25. What they're doing, Brad, is they're slicing the building. They're slicing the building into storage area, into a drugstore, into an office. That's how you should do it. We should, if you have an area, you should slice it. What I told you guys, what I do at least, and a lot of engineers do, if the majority of the building in an office building, as in like the building that we have, it is an office building with supporting areas, as in bathrooms and hallways and mechanical room and shipping and handling room. Everything, these are support areas for an office. For the most part, the building is an office building. So I multiply it by, what is it, 3.5, I remember? 3.5 volt-amp for all the lights. What they did here, they went and sliced the area. So they took the shipping and handling and call it storage and multiply it based on the table of 0.25 and add them all up. They just sliced the area. That will give you a smaller size. But honestly, it's not worth the work. It's not worth to go like the shipping place, Spencer. We could have taken the shipping and space. What was it? I think it was like say 10, maybe 15 by 10, say 150, 200 square foot. You could have taken the 200 square foot and multiplying it by 0.25 and adding it to the rest of the lighting load. In my book, it's not worth doing the splitting here. If the majority of the building is an office building, apply the office rule, which is 3.5. Any question about that? So but read it, please read it, because you might have an area where half of the building is storage. Half of your building is storage, like if you have a storage building and you just have one tiny office and in it, tiny little office, and the rest of the 90% of the building is just a storage. So in a case like this, it makes a whole lot of sense when you size the light for this area to multiply by 0.25. They're doing it by meter too, if anybody's interested in working in the meter system, which is not really a big deal. The window, the show window, we talked about the show window, guys, and the show window, 200 volt-ampere linear foot. So your show window in your drugstore that you show all the good stuff, measure it horizontally, linear, multiply by 200. And that was in the sheet that I gave you too. It's nothing new, I think, anyway. Receptacles, we talked about, guys, the receptacles and finding all the receptacle calculation and applying the rules for the receptacles. 180, if it's one, all these 180, and this is 360. Quads is 360, right? And we talked about this one. So assign it. Most of the time, guys, you're either in a commercial building, you're 90% probably were here, rarely here, and probably if I were to put a value on what you do, probably I would say 80% you're using this, and maybe the 20% using quads, and maybe a few fraction percentage using a one receptacle. And the calculation is always 180 per yoke. The yoke could have 2 receptacles or 1 receptacle. Damp and wet location. If your fixture is damp location, it has to be rated for damp or wet location. Fixtures. Signs. Remember the sign, what we talked about the sign, guys? It allows 1200 volt amp. And DJ, you're going to say, Chad didn't teach me that one. What did we do? Because it's continuous load 1.25, right? We multiply, if you guys remember, 1.25, and we moved on in that one. So that's what they're really doing in this chapter. And please, for your own sake, just read it one time. Please read it. Really. You guys, one day when you graduate from here, you'll, like everybody else, you'll standardize in certain sheets that you use and you continue with it. But it's really nice, as long as you're wasting your time with Chad, might as well use it wisely and read it. Appliances, motors and appliances, guys. We talked we talked about HVAC equipment for motors, especially for motors. We said 1.25 times full load current largest plus others, all others. That's how we size them. The HVAC equipment, we took the largest of the heating or the cooling, the largest of the heating and the cooling guys, and we added it. For appliances is, if it's continuous load, 1.25 times the full load current of the appliances. So we added all these stuff, if you guys remember. Especially the motors and the HVAC equipment. Motors, 1.25 times the largest, plus all the others. We added them up. HVAC equipment, we looked at the heat and the cool, and 99% of the time in Minnesota, the cool, it will be the largest, because the way we heat their homes is natural gas. I don't know about other states, but at least here, 99% of the time, your cooling is going to be the largest because of chillers, you know. So they kept adding these guys, and this split here, they went into it. I really don't want to get into that one. So for the hermetic motors, they split the hermetic motors, guys, into the pump and the evaporator and the condenser. Don't even mess with that one. Really, it's not worth messing with that. So basically, this inside the machine, they slice it into different motors when they size it. For all practical reasons, guys, if we have a chiller, and I'm going to show you an example of branch circuit for a chiller. How do we size the branch circuit of a chiller? But if we have a chiller and we need to add the load for the chiller, the full load time of the chiller, the rated load amp of chiller multiplied by the voltage, multiplied by 1.73, done. Don't get into what's the full load of the evaporator. That's how they find. They use all this to come up with a rated load amp. And Spencer, if you go back to your sheets, the cut sheets that I gave you about the chiller cut sheets, that you'll find I highlighted for your rated load amps. That's how they calculate the rated load amp for the equipment. And this is what they're trying to do. There's a condenser, you know. We look at it from an engineering point of view. We look at it as a big fat box here. All this stuff, and we need to power it, guys. A big fat box with manufacturer rated load current, and say the rated load current is 35 amps. That's all what I need to know as an engineer and a designer for this equipment to size for it. But what they're doing is not rocket science. What they're doing, guys, is they're treating 1, 2, 3 as a 3 motors on one feeder. How do you treat 3 motors on one feeder? You take the largest motor multiplied by 1.25 plus the full load current of all the other motors.
Yeah, but doesn't it matter, like, I mean, for when designing it, for controlling it, you have to know that? Because would that be a low voltage?
If you are designing the equipment, yes.
What about power?
If you're powering the equipment, no.
You don't have to worry about switching
the
relays and stuff in there?
No,
It's all on low voltage.
You have a big box chiller with its own controller. Again, I'm looking at as a designer, construction designer. You have a big box with a controller. My job is to bring a feeder to this box and a disconnect and an overcome protection device. Now, if you're designing this box, getting into the guts of the box, that's a whole different story. If I want to design what's inside the box, then you get into, is it single phase, is it 3 phase, and
so
so
it's
forth.
the HVAC guy on a commercial job that's going to be installing all the control switches for it.
These really come, all this info come pulled to a controller that comes with the equipment. The HVAC guys really don't even wire it internal. They bring the external control class 2 circuits and they tie it into terminals provided in the controller. So all what they do, everything internally even is wired for them. All what they do is they bring the external control wires and they tie it into predetermined termination blocks inside. They're not going to go rewire. Everything is rewired
No,
inside.
I just wondering about the control.
The control, there will be a controller over here. All the wires that you need to control this equipment will be pulled to a termination blocks, and I identified where you bring the sensor 1, sensor 2, thermostat 1 and 2. You pull them all into that termination box based on obviously how the system is going to be controlled. And then you program that control box to get you heat and cool and so forth. That's as far as I can get there. But this is a whole, I'm not minimizing it, it's a whole science by itself, pulling it. But guys, what we train you here, Dunwoody, for as far as we're concerned, we're only interested in bringing power to the equipment. 1, 2, 3. See, Spencer, that's where you start. That's what I'm bringing to this equipment. And I need an overcome protection device for this equipment, overcome protection device. And you might have to have a disconnect right in here to disconnect it if it's not part of the equipment. Some equipment come with a disconnect. I size my disconnect, I size my cables, my overcome protection device, done deal. If you are like Egan and you work in a group that has low voltage, then they get you into not even wiring the equipment internally, just pulling the low voltage between chiller 1, boiler 1, chiller 2, boiler 2, all the thermostat, zone control areas, and they pull all these wires into the controller of that chiller. I'm not minimizing it, it's a lot of work and a lot of coordination between these equipments. What they do most of the time is they pull information from this controller, I don't want to go there, into a building automation system, pull it, and right there they control the whole system. If you have multiple chillers, pull all this information to building automation system, and that's how you turn the chiller on and off, and turn the boiler a little bit on to compensate and so forth. Any questions about that? But our interest really is wiring this equipment or sizing the equipment. Okay, so basically that's what this chapter, it just walk you guys through the load calculation for that particular load that we did, or that particular project. Any question, my friends? Brad, any comment? You're smiling? I can't aggravate you now, man. So scared. What's serious? What's
Nothing.
Any question? Any question, my friends? We will be doing a load calculation review. Just if you're laughing at this one, because I'm going to be testing you guys. So next week I'm going to go what I did today step by step because of the test. So we will do that for the review. And I believe, and correct me if I'm wrong, we went through it. You guys did it. So I'm not really trying to rush it. It's really good. I believe we cover good of it. But I'll be reviewing it also for the test because we're going to be tested on that. More depth than what they did in this chapter. Okay, so that's basically what I wanted to do about this chapter. I want you guys to just to look at, please look with me at page 34. If you look at page 34, they have a unique way of doing the load calculation. Page 34. In page 34, they have a unique way of looking at the load calculation. That's another way of doing load calculation there. And again, another way of doing load calculation. So if you guys look at the drug loading schedule, we have the general lighting. This is just for the drugstore. We have the general lighting. We have count how many fixtures. Remember, as Spencer, we said for lighting, we do two calculations, guys. You guys remember? We did one based on the code and one based on actual. So they did the same thing. They did based on the code, see what it says, NDC code, and they based on actual units, and they calculated them, and they choose what part of it. What I didn't do is they choose what part of it is nonlinear, so you don't derate the neutral. What we did, guys, is we said we're not going to derate the neutral anyway. So that's if you look at Spencer, if that bothering you here, this is just to calculate the neutral, tell you, hey, you have this amount of nonlinear load, meaning you don't need to derate it for the neutral. That's the only reason why they have this. And then they have a balance and unbalanced to tell you how balanced your system is. Anything three-phase is balanced, anything single-phase is not balanced. Anything three-phase only is balanced. So all the chillers, that's what they split it. We did not split it this way, guys. What we did is we add them all up, and then we're assuming, obviously, you will, and they are assuming that you will balance your lights. You have to. If you use guys circuit 1 here and circuit 2, guess what? You already balanced it just by taking 1, 2, 3. You balance the lighting load right into phase A, phase B, phase C. Okay, so for the storage, they have the light, and they did the same thing for the storage. They calculate the light as well as other loads. Look at the receptacle, 21 receptacles for the other loads. At 180 connected, they call it connected because we need to derate them. And if you look at, they added them all up, they add the sign outlet here, which we didn't do. We put the sign outlet guys separate. And I don't want you to get confused. Please do it my way. Please put the sign outlet as a light. Okay? They have a roof receptacle. Brooks, they decided to have a roof receptacle for the mechanical equipment, and they gave it 1500 volt amp. That 1500 volt amp, by the way, it's designed. That's from them. They decided to do that. Okay? And then they added them. And motors, look at the air conditioning. We have the air conditioning, the compressor, the condenser, the evaporator. I didn't splice the air conditioning guys into compressor, condenser, evaporator, and you normally wouldn't do that. You have a chiller, one loaded amps directly for the chiller. And then they added the load and they divided it at the size. You look at the calculated load, is 23, almost say 23,000 volts, and you divide it by the voltage. If it's three-phase 2A, and that will get you the size of the panel for this load. The size of the panel for this load. Exactly, not exactly, but very similar to what we did. We added like lighting receptacle and other receptacle. We added all the lighting load. If you guys remember, we divided by the voltage to 120. We sized our building. Any question, guys? Anybody, if you read them, Spencer, you read that chapter. Any question about you there? Just any question?
The homework at the back.
The homework is for the homework, guys. I know, especially in page 39. Page 39. Can you look at page 39 for homework? The homework using the load calculation here. Here's what I'm going to ask you. I will give you the answers for this based on what they did it. So please do your best on it, and don't. How am I going to say it? You really don't. They're doing it a certain way, not different from what we did it. But do your best on it. I scanned all the homework and I'll give it to you, especially the calculation part. Okay. Because they're trying to do it connected and not connected and balanced. But really, that homework at the bottom, Spencer, right here, is really what they're doing right in here. And if it's linear load, if it's what makes a load a linear load? If it has a balance, if it's fluorescent light, it's a linear load. That's what they're doing. Anything that has a balance, any fixture like style I luminaire, if you dig through it, style I luminaire is a fluorescent light, and it's a non-linear. Okay, so I will give you the calculation, especially the calculation, guys, on the back of their book. Any question, my friends? Any question about this? The same thing, Spencer, about question number, especially chapter 4. I really don't want you almost to do the chapter 4 calculation because they're doing it in an awkward way. Anybody did chapter 4? Chapter 4 calculation? I'm not saying it's a wrong way, but it's an awkward way. Chapter 4, when you guys don't have a break, I want you, this particular one, they're doing it they're mixing a lot of things together that makes it confusion. I'm going to display it for you guys in a really 3 simple things to use. So, okay, that's basically what I'm going to be doing. In chapter 4, before I let you guys go, and when you come, I really want to do these 4 circuits, but I want to show you in chapter 4 a couple of things. And I'm going to go all the way. This is about branch circuit. We know how to use 310-16. Anybody does not know how to use 310-16? Just a reminder. No? Spencer? No?
I'm okay.
Okay. Just a reminder. 310-16. If your equipment amp is 100 or less, you use which column? 60-degree column. If it's more than 100%, 75-degree column. If your conductor size is number 1 or less, you go to 60-degree. If it's more than number 1, you go to 75. That's it. That's all what you need to remember on using 310-16. And a couple of other things, guys, is number 12. No matter what you do, number 12, you cannot break for lighting purposes. You cannot break number 12 with more than 20 amps. If it's number 14, drop number 14. Don't even think 14 when you talk about commercial. Don't even think that word 14. If you have a 30 amp circuit, you cannot. If you have a number 10 conductor, you cannot break it for more than 30 amps. And this is only for receptacles and lights. If you have a motor, you can. And I told you guys, motors are exception. Motors are exception. I can have a motor, 3-phase motor, powered with number 12 conductor and the overconduction device. The conductor is number 12 and the overconduction device is 50 amp. No problem. Because motors have an inrush and motors are protected by overload. Motors are an exception for that. So that's basically what that thing is going. It talks here, guys, especially for the installation, it talks about not mixing aluminum and copper and marking for the conductors and the circuits and so forth. CU copper, ALCU copper conductors. Almost always, guys, all your brand circuits up to probably 30 amps, all of them are copper. You're not going to see a number 12 conductor aluminum. This becomes a big deal if you have a chiller. If you have a chiller and you're going to bring a feeder 4-aught aluminum feeder 4-aught going to the chiller, and the chiller, guys, the termination on the chiller will tell you that the lugs are rated CU or EL, so you can land a cover on it, especially major equipment, or you can land aluminum in it. So, and all these panels like this, the panels, they're rated, the lugs here will be rated aluminum or copper, so you can bring an aluminum feeder and feed it from it, or a copper feeder. You can't mix the two together, right? We can mix them together, two feeders, but we can bring either or. The lugs are rated for either or. So that's basically, and this becomes an issue only for feeders, or brand circuits, major brand circuits, as in going all the way, like 100 amp or more. Yes, sir?
It was only rated for aluminum and or copper, and you brought aluminum with paste. Is that legal?
Aluminum with paste.
No.
I don't know. I really don't know.
You know what I'm talking about? The paste that you have to put on aluminum?
Yeah, this is for the torquing. Don't they use that for torquing?
No.
But the lugs,
So it doesn't
the corrosion, oxidation, yeah. But the lugs itself have to be rated for that, though, for aluminum. I've seen it. Yeah, yeah. But it's for torquing and for corrosion, you say. But I believe that lugs itself have to be rated as either you bring, not both, either you bring this or that, either this or that. If your lug wire connector, look at the wire connector, it says CU. Look what they're saying. If it says CU, what do you need to bring here? You need to bring CU only, copper only. So this is what you're going to be, copper or aluminum or a mixture of copper and aluminum. Copper-clad aluminum, guys, is, I think they have 10% copper and 90% aluminum, copper-clad aluminum. Any question, guys, about this? So this becomes an issue with feeders. If you have feeders, it becomes an issue. Almost all equipments, guys, at bigger sizes are rated a copper or aluminum, bringing to the feeder copper or aluminum. Any question? I'm sorry, sir.
In the commercial, we don't use number 14, we don't use it, right?
You don't want to use number 14 design-wise in a commercial building for voltage drop. But that's not code, though. That's not code. You can use number 14 code. But minimum engineering-wise, and a lot of specs guys would say engineering-wise, minimum conductor that you can use number 12. It's not worth putting number 4. Commercial building, I can't emphasize, we're in the commercial now. Okay. Dual rating and all this stuff, we'll talk about the sizing, guys, when you get back. I want to be talking about, where's the sheet that I want to, okay, here you go. This is the one that I want to, when you guys get from the break, this is the one I want to emphasize. We're going to, when we get back, I want to emphasize this particular one here. So we're going to take a continuous load and size the overconduction devices. I'm just going to review before I go. If you have a continuous load, guys, the minimum allowable ambicity is 125 times the load, and the overconduction device is 125 times the load, right? That's if it's continuous. If it's non-continuous, it's just jump to the non-continuous. If it's non-continuous, you don't have to multiply by 125, right? Look here, the difference between continuous is 125, non-continuous, you don't have to go 125. Let's do the motor, and I'll get back to the other loads. Let's do the motor. The motor, guys, always the conductor, as we learned, 125. Now, the overconduction device is different. Your overconduction device motor, your overconduction device is different, and I'm going to change this one most of the time. It's going to be 250 molded case circuit breaker, 250 molded case like these ones, molded most of the time. Unless you know otherwise, the assumption is molded case. So 250. If you have a chiller, this is your chiller. If you have a chiller here, a chiller, guys, the same thing, continuous load, and the overconduction device most of the time is 175 degree load, 175 percent. So, any question guys about these? These are, I'm going to take a few examples when you come back. I'm going to take a few examples about this. I want to emphasize continuous, non-continuous. And when I say continuous, non-continuous, these are not motors. These are lights and receptacles. These are lights and receptacle loads. So if anybody says, well, what is this, Chad? So this is going to be, it could be, these loads here could be receptacle or light, most of the time. And also the non-continuous here could be receptacle or light. Or other equipment, the non-continuous, right in here. Motors, we know what a motor is, a pump. We know what a chiller is. Arc, cord, and plug branch circuits, you really would, not less than overconduction device if you're plugging equipment, cord and plug branch circuits. It's not going to be, if your branch circuit is cord and plug, it has to be rated for that. The cable have to be, don't look at this one, but it has to, the overconduction device and the conductor have to match the load. No 1.25. One thing I didn't talk about, that max business, right? I'm going to talk about the max in a second. Any question, guys, about continuous, non-continuous motor or hermetic motor, which is the chillers? Any question about this? Yes, sir.
It seems like in commercial, you'll see a lot more big machines with a cord and plug on them.
Cord and plug, then the cord. If you have a cord and plug machine, the cord itself have to match the load of the machine, and the overconduction device have to match the cord equipment. Cords, guys, you don't have to, all rated. If the machine comes with the cord, if the machine itself comes with the cord, and most likely, probably they take, if it's continuous machine, they take this 1.25 into consideration. But it's a cord machine. The cord rated for the machine and for the overconduction device plugged in. Any question, guys, about continuous, non-continuous, hermetic, and motors?
But you'd still be rated if it's still too far.
For voltage drop?
Okay.
Yes. For voltage drop. And when cord, I don't want to get into cord, guys, because it has its own tables in NEC code book. If you have corded material, if it's not hardwired or if it's not flexed, you don't even use 4 cords. We don't use 310/16 for cords. We have a whole table that talks about cords, a cord connected to a machine plugged into the wall. All the calculation that we will be using, guys, it's basically wiring the machine either with EMT it to a box and then flex it directly to that machine.
You're not going to be able to plug it into a receptacle that's not rated for it anyway because the plugs are different. It's a
50,
amp,
yeah,
it's got
50,
a different
yeah.
plug than a
If you have a
50
50 amp machine, 50 amp 3-phase, the plug will be 50 amp, the machine will be 50 amp, the cord will be 50 amp, and the cable coming to it, the circuit will be 50 amp. So all rated for that particular. The last thing I want to say, guys, is max. If you guys remember, next, now if I want to emphasize, if you did the math and you couldn't hit a standard, max, you can go next higher, as we know, we're going to be doing that. In compressors, if your compressor doesn't work, they allow you to go another 25%, 225% up. And if you have to go down, if it's not a standard, If it's non-continuous load, you can go to the next standard. If it's not standard, in motors, they allow you if your motor doesn't run. And I don't like that one because if you look in the code, guys, there's multiple scenarios. There's more scenarios than just the 400. If you size based on 250 and every time you turn your motor on, the circuit breaker trips. They allow you to go as high as 400 on a molded case, if I remember right, circuit breaker. But day one, guys, you don't care. Day one, you're going to size based on this. And the same thing, that guy is not higher than that if it's a cord. But my interest mainly, as I said, is only in the first three or the first four. Any question, guys, about that? Continuous, non-continuous, motor, and chillers. Any question, my friends? Now, this is what I don't want you guys to, you're going to see in the book, guys, they define it by columns. That's probably, if anybody read the chapter, they define it by columns and what's the amp and what's the key. And they have a whole lot of, I'm going to look at the book because it makes more sense here. This is, it's up to you if you guys want to do it. Go ahead and do it. But I'm going to show you how I would do it, which is very similar. So if you guys just do me one favor, go to page, one favor, and I promise it's a Friday and I'm not going to make it too hard on you. Page 54 and 55. Page 54 and 55. This is the author's way of doing branch circuits. The author's, Spencer, it's this author's way of doing branch circuit, which is like what we did, but he has his unique way of doing it. If you look at phase connection, you have circuit number one. They're talking about the panel board worksheets. We have circuit number one. It has 9 style I merchandise areas. So we have 9 lights on it. I'm reading guys the first line, the first column. All these lines together, calculated volt-amp is 783. So they added the volt-amp for all these 9 fixtures. Does that make sense? They just add them up. And then they divided them, calculated amp. They divided the volt-amp by the voltage, and they came up with 6.5. Everybody knows when we came up with 6.5. Just divide it by 783 by 6.5. Okay? Then load type is continuous. From what we see is continuous. Our receptacle is continuous. Load modifier, that's what I don't like because he adding them all. This, if it makes sense to you, load modifier meaning because it's continuous, Spencer, you have to multiply. I'm reading, by the way, at page 55. I switched into the upper right corner of page 55 because that's how it continues. Load modifier type is C. Load modifier is 1.25. Overcomputation device or overcurrent selection current. This is, you take the 1.25, multiply it by the full load current. So you need 9 amp cable. Overcomputation device is a 20 amp because we don't want to use less than 20. It's a commercial building, remember. And the conductor size is number 12, right? Because we could have done with 14, by the way. Look at the 9 amps, but we don't want to do that. And then the amplicity of the conductor is 16 amps. If it's continuous, how much current you can get out of it? Number 12 if it's continuous load, 16 amps, based on 20 amps. And then the risk is I don't like, guys. Then the ambient temperature that we calculated, all this is at 30. What the author guys did is he mixed the derating with the continuous load and with so derating and continuous load all in one. So now he thinks, okay, now what if we need to derate? So if the ambient temperature is 30, so I don't need to derate. The correction factor is 1, so because the temperature is 30, no derating based on temperature. And they have current carrying conductor adjustment factor. Oh, current carrying conductor means what if you group them more than 3 in one circuit? We're not grouping, so there is nothing to group. And adjustment factor based on grouping is 1. So the allowable amplicity continue to be 16, and the conductor continue to be 16. And the allowable amplicity for number 12 is actually 30 amps. You can get 30 amps, and the amplicity is 30 amps. So, and you can go through it, guys. They have continuous load, they have receptacles, and they have motors, and H, the hermetic motors, the compressor. What I want to do, guys, is I want to size them, as I said, based on continuous, non-continuous, and so forth. And I want to mention to you what would you do if you have a derating and so forth. Okay? Shall we have 5 minutes quick?
No, you know, not even that. Yeah,
Yeah.
maybe that.
So, if, you know, just because they have a cord, if I understand the cord and plug, say it's 30 amps, you know, it's, if that is a machine, and then if you're going like 200 feet, you consider the volt, you got to consider the volt drop is calculated in there and everything else, just to make sure, I mean, you're still looking at that plug.
If you have a 30 feet cord,
No, I'm not looking at, I'm talking about the feeder.
on the
From the
feeder, yes.
panel.
Yes, you have
From the panel, is this, you still do all this the same, right? I mean, to make sure that you got a carbon after, I mean, say it was going off the roof, you'd have to be rated, you have to have the
Yep.
wire or something. You still do all that. We're literally, okay, so this is just saying that you just go from the plug to the machine for what it says.
Yep.
That's all it's saying.
Yep. From the plug directly to the
There's just a thing, shopping with the calculations, if you got a cord on it.
With cords, they get you how much voltage drop you can drop on the cord. The
Oh, yeah, that's all
manufacturers.
calculated in the cord then, right?
Yeah. I believe.
Well, they designed them.
Really want to hear the recording here? Okay, so let's say number one. Number one as non
What are you going on?
continuous load.
What are you going on?
What do you mean? Oh my God. This is just summarizing what we did in chapter 4 in my book in an easier format. Okay? So, if that makes sense. A couple of examples, guys. Really a couple of examples. I have a non-continuous load. An example for a non-continuous load for you guys would be what? Anybody can come up with a good example in a commercial building.
Receptacle.
Receptacle right in there. So if you have receptacles, an example is receptacles. Receptacles. Basically, a good example of receptacle, but it could be anything that runs less than 3 hours, right? Everybody, that's the definition. 3 hours or less, or more than 3 hours. 3 hours or more, or less than 3 hours. So, for the most part, we're talking about receptacles here. We're really talking about receptacles, or or any machine that does not run 3 hours. So, I have a quick example here for you. I have an overcompression device, and I decided to have a machine. This machine is non-continuous machine, and I bought it from China, and they gave it to me for 32 amps. It's rated for 32 amps. Machine, not a motor. I shouldn't probably use the symbol of a motor. It's just a machine. It could be anything. Machine, and 32 amps. Non-continuous machine, 32 amps. I need to wire it. Non-continuous machine, 32 amps, I need to wire it. Non-continuous machine, 32 amps, I need to wire it. Keep stuck with it, huh?
What about 32 amps?
Alright, here's what we need to do. I need to size, number one, guys, the conductor, and number two, the overcompression device. Let's do number one. Number one is the conductor. If it's non-continuous, you take the 32 amps, take it all the way to where? 310.16 under which column and why? 60-degree column, and that will get me 32, number 8. Number 8. How many conductors? Number 8. How many conductors? Anybody can tell me how many conductors? Depends upon the voltage, and it depends upon the phase. So that's a nice thing, guys, about this calculation can apply for any voltage, for any phase, or 3 phases. If it's for any voltage, if it's a 3-phase, does not need a neutral, then it's 3 conductors, guys. Okay? So this calculation, again, apply for anything that you want it to apply to. Okay, let's say, so this is number 8 AWG. Number 8 AWG. How many conductors depend on the equipment? Since we are commercial, let's use everything right now, guys, a 3-phase. Let's say that was a 3-phase. So how many conductors in this case? It's most likely 3 conductor, number 8. No problem. The second thing that we need to do is the overcome protection device. Number 2, this is the conductor. I should have wrote conductors or branch circuits. Branch circuits is the more sexy word for them. Overcurrent protection device. Sizing the overcurrent protection device for this piece of equipment, which is number 2. The same thing, guys. It's 32 amp. Take it all the way to 240.6. What's your next standard overcurrent protection device? 35, Brian? 35? 35 amp. The next, and you go up if it's not a standard. If it's not a standard, and that's what we just showed you guys the picture before. If it's not a standard, we go up. Any questions? Straightforward. So if you have a branch circuit or a feeder in your building, a machine, non-continuous, that's how you size it. Non-continuous, directly based on the amps. Any question? So that's scenario number 1. Scenario number 1.
Wouldn't,
So,
if that's 3-phase, would that be 4-phase?
we're not pulling in neutral. If it's a 3-phase machine, guys, most likely 99% of the time a neutral is not existence. That's the reason why we use 3-phase. How would I know if you really don't? But so your question is completely valid. 3-phase only. Any question, guys? Any question about that? Any question about that? So this is, if it's a machine, non-continuous. The next one I'm going to do, guys, how about if I want to see, I need a receptacle circuit. Now I'm going to start, you guys are going to be circuiting for me. I tell you I have multiple receptacles in a commercial building, and I'm not telling you the criteria. By the way, the project that I'm telling you guys that we have has a criteria for circuiting. No more than 6 receptacles in one circuit. If you don't have the criteria, how would you do it? So here's my next example. Hey, bud. Example number 2 is receptacles. Receptacles, and we are still under non-continuous load, guys. We're still under the non-continuous load. So that's still number 1 here, or non-continuous load. Here's my question. I'm going to start this one in a different way. I have a 20 amp number 12 conductor, 20 amp number 12 conductor, receptacle circuit, and I need to know how many receptacles I can feed, and I'm only showing the phase. How many receptacles can I feed from one 20 amp circuit? 120 amp, 120 amp circuit, and the voltage is 120 volt. The voltage is 120 volt. See how I'm looking at it differently now. Instead of sizing the cable and the overcurrent protection device, Brad, we're going to size how many receptacle circuits, guys, are always 20 amp in a commercial building. How many of them can I put? How many of them can I put on one circuit? Okay? Okay? All right, so number of receptacles, the number of receptacles. You're going to take the number of receptacles, guys, as it's non-continuous. These are considered non-continuous, remember. So you're going to take the 20, multiply it by what? The 120, and divide it. In a commercial building, every receptacle is assumed is going to consume 180. 180. So that will give you how much? 13 even, right?
13.3.
Yeah, so 13.3, and you drop down to 13 receptacles. Just keep this in mind. If these were convenient receptacles, that's what you basically would be sizing. If these were convenient receptacles, that's what you'd be sizing. 30 receptacles. Convenient receptacles. Okay, so that's best. Now
I
we
suppose they want only 6. It seems
that's
really under.
Yes, thank you. This guys, these are assuming it's convenient, sitting there, not energized, not used all the time. If it's in an office where people sit in cubicles and use them, they're not just convenient receptacles. It's almost dedicated receptacles. right? Because people can sit in offices. There is the rule, at least I want you guys to apply, not code, rule. And you can justify it by code. Then, for office receptacles, guys, any office type receptacles, not hallways. Anything where you have offices, cubicles, meeting rooms, all this stuff. Here's a design criteria. 50% of what you just came up with here, of 13, that will get you what? What's 50% of 13? 6.5? 6.5. And that obviously you don't have 6.5, so what do you need to do? You're going to go down to number 6. This is how the number 6 came to be, at least. Again, this is, can you put disclaimer here? CSK, that's my initials, disclaimer. If somebody tell you who the idiot told you that, just say Chad Curdy. I'm okay with that. So that's where you want to cut it. Why? Because of the use, guys. It's used more. So you kind of cut it by half, almost cut it by half. So that's why most of the receptacles that you see in our building, they're telling you 6 receptacles, no more than 6 receptacles in one circuit. 6. And when we see a receptacle, when I say a Spencer receptacle, I mean a yoke like this. There could be 2 receptacles, a duplex, or a single receptacle in one yoke, not quad. A quad is 2. So you can feed 6 duplicate receptacles from one circuit. Does that make sense, guys? Does that make sense? Okay. So 6 of them in one circuit. Okay, so that's basically where your receptacles are going to be fit from. Your 6 receptacles in a commercial building, office type. There's only receptacles fit from. How many receptacles do I have? Here's the fun part, though. Here's the fun part. This is phase A. Now, I'm tying it directly to what you guys are going to be doing. This is phase A. I want to go grab phase B. Okay, the same thing, guys. Here's phase B. And I'm going to grab phase C. And here's phase C. Okay, so and I'm not going to convince you that phase 1, 2, 3, 4, 5, 6. Bam, 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 bam. Okay, and phase B, the same thing. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right, 6 of them. So here's this is a 3-phase receptacle circuit. 3-phase receptacle circuit. See how I grabbed phase from every phase, phase A, phase B, phase C, and I fed these receptacles, one way of feeding them. Then, here's the fun stuff. Then you can share a neutral. Look what I'm going to do, guys. Very important here. I'm going to grab a neutral. I'm going to grab my neutral from here to here to here to here to here, and drag my neutral all the way back and call it neutral. And I'm going to steal it from here and go back again. How am I going to do that without making a mess? Here, 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 and here to the lights. And I'm going to steal it from here and go 1, 2, 3, and 1, 2, 3. Can you guys see that? So I stole a neutral. I have a multi-wire, 3-phase multi-wire receptacle circuit. That's exactly what you're going to be doing in a commercial building. Brad, in the open office area, they're telling us they want a neutral, or some application they want neutral per phase. You give them a neutral per phase. But if they don't tell you guys, the most common economical way of wiring receptacles is exactly what you're looking at. So how many receptacles in this 3-phase circuit now? 6 times 6, 18 receptacles in a 3-phase circuit. I use the term 3-phase. They're really 3 single-phase circuits grouped together and fit from 3. How many conductors? Look how nice. How many conductors this circuit will have then? 4 conductors. Very nice. 4 conductors feeding all these receptacles.
Because 2 of them cross each other all. so it allows it to have a third path or whatever.
Yeah, because the three-phase system, they balance each other to zero if all of them are running at the same load. Any question, guys? Any question about this? Does that make sense? So that's what you're going to be, Spencer, doing as you move through your build. That's one way of doing it. Another way, Brooks, probably some people will do, they bring phase A here, phase A, B, C, 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 and they stagger them. And that's a better way of doing it, more expensive. So here's, I bring a three-phase circuit right in here. I put this one in phase A, this one in phase B, circuit 1, circuit 2, circuit 3. Circuit 1, circuit 2, circuit 3, and you keep doing it. What's the disadvantage of this? You're pulling the more wires. What's the advantage? The advantage is, yeah, more power in one location. And that's what I want you guys to do in the offices as you circuit. Keep this in mind. If you have 3 receptacles in one area, feed them from circuit 1, circuit 2, circuit 3, and go to the next office, the same thing, feed it from circuit 1, circuit 3. That's the best way of doing it. Meaning if Chad is sitting right here, and Brooks' office is right here, Brooks is not here, and Chad is here. I have almost three circuits for myself here. A lot of power, right? Yes, it's shared, but it's highly unlikely that everybody that's using these short circuits will be energizing them fully at the same time, guys. So you take advantage of the diversity of the load. They call it diversity of the load. Highly unlikely that the people will be utilizing all these receptacles, all of them, fully at the same time. But it's highly likely that Chad Kearney will be plugging multiple things sitting in his office and goofing around here, right? One person. I can't emphasize this design. Is this directly related to how we're going to be circuited? Any question, my friend? Now, Mr. Bew, is it wrong if you want and put the, 13 receptacle on one circuit? It's not wrong. If they're convenient receptacle, you wouldn't probably, if they're hallway receptacles and convenient as just for cleaning and so forth. You can almost put 13 of them, but you really don't want to do that though, because to pick 13 convenient receptacle, not office type, in a building, you almost have to run the circuit across the whole building to pick these receptacles. It's not worth it. So it's not worth it. Any questions about this circuit? Can you please add this one to your reservoir wiring as we go through? That's exactly what I want to emphasize, non-continuous load wiring circuit. 6 receptacles. Is it wrong if you added a 7th one? Brad, as your circuit, there's a tiny little one. Should I pick another circuit? Let's throw it. Not a big deal. So don't take it like, if it's an 8 receptacles, guys, and I have to pull another circuit for only 2 receptacles, what would I do? I just put the 8 receptacles, put them in. But you don't want to put, I start worried if I have 10 receptacles or more. If you hit 10, split them. If you hit 10, split them, 5, 5. But if you have 8, close to 8, 9, you hit 10, just split them. Okay? But your rule should be kind of, the rule of thumb is 6 or more on one circuit. You make a lot of money out of this, DJ, huh? Okay, so that's basically the non-continuous load. Let me just give you an example of continuous load, guys. This is number 2. Continuous load. Continuous load, this is very good example is lighting. Lighting. And other machines. And machines and motors and all this good stuff. We're going to get into the motors, but machines, lighting and machines. Continuous load. Did they spell it right, Brooks? You guys are laughing at Chad here, and I can't even aggravate you anymore after that shooting. That scared me now. I used to yell now and just tamed down, huh? All right, let's take, here's an example. Here's my, I'm going to take first a continuous machine and then I'll take a lighting example, exactly like we did this. Here's a machine. This machine, let's power this machine. The example of this machine that I have, actually for continuous load, you know what? Let's say I have a machine of 133 amps, 3-phase. I bought this beautifully machine, 3-phase, 133 amps from China, and that machine welds and cut things and do all this stuff. And it's all what I care about is a continuous load. non-motor continuous load. Highly unlikely to find a non-motor continuous load sometimes. I have the rated amp on it 133 and they're telling me it's continuous load. We took everything into consideration. Just size for this. So, and that's what I'm going to do. Any question guys about this machine, continuous load machine? Okay, so as always, I'm going to go size number 1 and size number 2. So for number one is branch circuit conductors, the sexy term for it. Paul is not here, we can spice it up a little bit here. Branch circuit conductors. Oh, I'm recorded here. I'm going to lose my job here, man. Branch circuit conductors. If it's continuous, guys, everybody knows what do we do for size branch circuits? 1.25. Thank you. We're going to do a 1.25. Multiply that baby by 133. I do not have the example for this, so I need a gentleman or a lady, no ladies today, to give me the answers, please. If you guys want to go to lunch on time. Now I spice it up, huh? How much?
166.
166. 166 amp. Another gentleman disagree. You take this one to where? 310.16. Which column and why?
75.
Thank you. Why? More than 100. That's kind of the rule. More than 100. So 75-degree column. What's the conductor size and how many? 3 because it's 3 phase. What's the conductor size? Number 2 watt. That sounds about right. 2 watt. And Mr. Rabab, this is, believe it or not, it's a 2. It doesn't look like one, but it's maybe in Hebrew it looks like a 2, but it's a 3 2 watt. 2 watt. 3 2 watt. Okay, we size the machine. Up and running. We size the machine. Okay, the overcurrent protection device, the same way, guys. 2 overcurrent protection device. Most likely inverse type circuit breaker. And you're going to do the same calculation, 1.25 multiplied by 133 equal 166. Take this one to 240.6. And if it's not a standard, go up. And 166, 175, Brooks? Spencer?
Yeah.
175? Ben? I'm sorry, Ben. Yes. Everybody, you're saying the answer, and I'm just, my apology. 175 amp. 175 amp. Any question guys about that? Straightforward. You buy yourself a 170 amp circuit breaker, slam a 2 watt on it. How many conductors do I need? 3 phase. Why 3 phase? It's 3 phase, no neutral. Almost always, if you have a 3 phase machine, guys, almost always no neutral. That's the advantage of a 3 phase system. That's why we invented the 3 phase system, because we don't want loose wires. It's more efficient. Now, question for Muhammad, my friend. Do you think a circuit 2 watt, and anybody can help Muhammad jump in here, or Mr. Rabab or Camille, if you guys, is it a good idea to group a 3 conductors 2 watt with other 3 conductors 2 watt, group them together in one conduit? Or is it better idea to put them in one conduit, one feeder going to the equipment? One conduit, one feeder? Absolutely. If you guys grouping, when you go in the commercial building, guys, you're going to talk about grouping. When would it be a good idea to group branch circuits and feeders? When it's a good idea and when it's not a good idea? It's definitely a very bad idea to group anything higher than 100 amp. Anything higher than 100 amp, bad idea. That's like if you have a load that you're going to end up, the load is 100 amp or larger, and you need to group it with another 100 amp or larger. You can put it in a bigger conduit. Bad idea. You can, but it's a bad idea. So grouping in my why it's a bad idea? You end up with a lot of derating. You're going to derate the conductors, bigger conductors. From a reliability point of view, if you have a 100 amp load in your building, that must be a big important load, wouldn't you think so? 100 amp at 2.8, 1.3 phase, that's an important load. If you have 2 of them in one cable, guys, one of them shorted, most likely the other will go with it. So from a reliability point of view, reliability and maintenance and troubleshooting and all this good stuff, it's a good idea to separate CHED, not code or anything else. So I'm going to write a little bit of a disclaimer here, guys. a disclaimer. If you have a conductor, and I'm going to use this one because number 1 or smaller and 100 amp or larger, or 100 amp or smaller, group. You can group. If your situation, if you have a conductor number 1 or smaller, like number 12 and number 8, you can group them, no problem. It's a good idea to group them. You save money. If your load is also 100 amp or less, that's a good idea when you size a conductor for them to group it, which is basically the same size. Other than this situation, don't group. Does that make sense? Again,
Group in the pipe.
yeah, group them in the pipe. Everybody knows what I mean by grouping. You bring the conductors, right, and you have a 4-inch conduit coming here and feeding 2 machines. You can do that. J-box, big full box, and you can do it. Again, these are really not code. I like to pick the 1 and 100. Anybody knows why the 1 and 100? Because that's the cutoff for 60. So I like to stick in people's mind. These are where we switch to 70 and 60. So in this case, no, this is grouping. Otherwise, what's the otherwise? Otherwise is more than number 1. And or more than 100 amp. No grouping. No grouping. It's not a good idea to group them. It's not a good idea. Again, and next to these, please write CSK. My opinion. Opinion. Some people, guys, don't group even a 50 amp. If you have 50 amp load, don't group it. Just give it dedicated circuit. But these are the extreme. I picked the extreme. You know, you really don't want to go and group anything higher than number 1. You don't. Even if you can, you don't. For voltage drop, for derating purposes, for multiple derating purposes. Having said that, I want to go back here. Can I group here? Can I group based on that one? Can I group this circuit with another 5 circuits like it? No problem. In one 3/4 of an inch is that 3, half looks like a 1/2 inch EMT conduit. Can I group them if I can fit them? Yes. So I can group. If you group, Mr. Bew, what do you need to worry now about? That's what chapter 4 is talking about. Derating. You're going to worry about derating. So, and we'll do an example about this one with the grouping, not today. So. Any question, guys, about this? So that's the continuous. Let me do the lighting load. I know it's Friday, but bear with me. Any question? Please write this disclaimer, guys, about grouping, when it makes sense to group and when it makes not sense to group. Another bad idea to group if you have a temperature issue. If you need to derate based on the temperature, it's a very bad idea to group, because you end up with double derating and a big fat conductor that's carrying nothing. So, but most of these equipments are inside. Temperature is not an issue. So we can derate. Temperature is not an issue. Okay, the second one is lighting. I'm going to do an example about lighting. Lighting, branch, circuit. For this, again, we're still in number 2, continuous load. Lighting is continuous load in a commercial building, so get used to it. Lighting is a commercial load. So I'm going to go, guys, with here's my circuit and how many lights, and I'm showing here fluorescent lights, but they really could be any type of lights. How many lights I can feed out of the most common one is a 20 amp and number 12. How many lights can I feed from a 20 amp number 12? 20 amp number 12, right? How many lights can I feed out of number 12? 20 amps. This is a little bit challenging because the Volt-Ampere lights brooks are different, right? I can't find a Volt-Amp. Light number 1 is a 100 volt amp, light number 2 50, light number 3 30. So it varies, right? It varies. What I'm going to give you guys is a practical example based on experience, and you can use anything. So let me see how many lights. The assumption that always the worst scenario. I use this. I use the worst scenario assumption is I'm going to assume every lighting fixture is going to have 180 volt. But that's really bad assumption. That's the worst that you could find. 180 volt. So I'm going to assume that this fixture is actually 180 volt. Okay? And let's do the calculation then. Piece of cake. We've just done it, right? Number, Volt-Amp. Yeah, this is Volt-Amp. Number of fixtures equal. If it's continuous load, what do you do with the amps for the circuit breaker? Cut it by 0.8. So you take a 0.8, multiply it by 120, and divide this by multiply it by 20 amp. And let's do it the proper way. The proper way is 0.8 times 20 amp times 120 divided by 180 volt. Anybody can get me how many fixtures you can put in that 20 amp circuit? Oh, why do I throw the 0.8? It's continuous load. Continuous load, you can't pull more than 80% in a circuit breaker of continuous load. Circuit breakers are not rated for more than 80% if the load is continuous.
Oh,
It's continuous load. Lighting is continuous load. I'm sorry, what did you say? Is there a fraction?
It's 10.6.
Okay, that's what I want. 10.6, and that will drop you down to how many? 10 fixtures. So that will drop you down to 10 fixtures. Huh? I'm sorry, what? A low count? Yep. That's based on the worst scenario that you can encounter, which is 180. 180. Okay? That scenario based on the worst scenario, 180. 10 fixtures. 10 fixtures. Now, let me give you, if you know your lights, Brad, if you know your lights, this is the worst scenario you're going to have. The second scenario, and fixtures, I'm sorry guys, fixtures are different. Let me give you the second scenario, that 20 amp, number 12. If you're using fluorescent, like right above your head, and typical fluorescent, typical lights, on average, most of them are 100 watt or less. Most of them are 100 volt amp or less. So on average, the second scenario guys is 100 volt amp or less. Okay, let's do the calculation based on 100. So we have number of fixtures equal 0.8 times 20 times 120 divided by 100. How many do you get? Anybody? Ben, where's your calculator today?
It's right here, but
0, 0, so that will get me to, so 24 times 0.8 is what? Come on guys.
it's 1920 divided by 100, so you get 19 pictures.
19, what's the fraction? Thank you. 19.2, and that dropped you down to 19. That more in the ballpark that you do?
Yeah.
More.
The 32 watt units.
Yep. Absolutely. That's exactly based on assumption of fixture right above your head, and that's not a bad assumption, guys. The first one is the worst extreme scenario that you can encounter. To meet the energy code, and I want to highlight that one. To meet the energy code, you almost are in here. So I'm going to highlight this one and keep it in your mind. This is how many fixtures you can put on the lighting. So can you use this one as your design criteria? Unless you know that your fixture are higher than 100. So almost, Spencer, almost always when you look at the fixture volt amp that we're going to be designing, almost always they're going to be 100 or less volt amp when you take the volt. So unless you go to a parking lot are different. The volt amp parking lot 250. So you might have to treat the parking lot different. Manufacturing floor guys, when we use high intensity discharge, these are 300 volt amp. So 300 volt amp, you might have to do the calculation on it. But typical office type lighting, you are right into this scenario. Right into this scenario.
That's why you came up with 100 that you put in terms.
Well, typical. typical. The first one is the extreme scenario. The extreme scenario is, and I used to push that one, but with the energy code, guys, with the energy code now, you can't meet 180 volt amp, put 180 volt amp lamps in your fixture and meet the energy code demand. You can't meet the energy code, so you're almost cutting you down to 100. So, so how many fixtures you can, for our project? 19. 19. Do you have to go 19, guys? If you have 20 fixtures, always split them. Always. What I would do, guys, if I have 20 fixtures, split them into two. I would split them into two. I wouldn't load more than 19. I would not load more than 19. Because remember, the first one, the receptacles, we cut them by half. But here's no cut. We're loading the circuit up to the 80%, almost. So if you end up with 20 lights, I would put them in two circuits personally. Is it wrong if you put them in one circuit? No. But then you loaded that circuit you can't add anything to it in the future. There's no future expansion in the circuit. I mean, we didn't see anything about future expansion here either. So, any question guys about this circuit? The lighting branch circuit. So now we know how many circuit we can feed. Okay, I'm just going to draw, I'm going to draw one little thing, guys. The three-phase system, how the three-phase system is going to look like. Here's my three-phase system. Most likely, you're going to end up with, here's a phase B, and I'm going to go grab phase C.
So you're going to use the 180 if you're possible future expansion?
If you have future expansion, you probably will cut. If I know fixtures, guys, there's not a whole lot of future expansion, really. What are you going to expand on there? So you're going to add another fixture. A 19 adding a 20 is not a big deal. That's why I said cut it if you don't go more than 19. Receptacles, I can see how things can load changes constantly in receptacles. Lights, you put these lights here and they stay forever almost. And if you remodel the building, guess what? You remodel the branch circuits. If you do remodeling in the building, you remodel the branch circuits. So here's another circuit. Here's another 180, which could be any one of them, guys. So and then the best scenario again, and I know the harmonic and all the stuff is to bring in neutral and neutral and neutral. So here's your three-phase, 4-conductor, number 12, three-phase lighting circuit, and you can feed from these based on the scenario. The second scenario, guys, 20 times 3 is 60, minus 3 is 57. 57 fixtures, 57 fixture from 4 conductors, number 12. That's a lot of fixtures. That's a lot of fixtures. Now there's the harmonic issues and all this good stuff. The ballasts are getting more and more better with the energy efficient ballast and all this good stuff. Some engineers, guys, if you group the neutral, I know some engineers will go and knock this number down by 0.8 just because of grouping the neutral now. We're grouping neutral, so knock it by 0.8. Some engineers will say maybe the neutral has to be number 10 if we have high harmonic. But personally, if you're carrying 19, it's highly unlikely all the 19 will be on all the time and fully harmonic and so forth. So probably you can get away with number 12 can get you 30 amps, guys. That's what people don't understand. Even if you double the amount of current on number 12, you can get you before it starts smoking. You can get 30 amps out of number 12. Not legally, but it's handled 30 amps before it starts smoking. So even if you double the load on the neutral, you're still in a good shape. So I could, unless you're told otherwise, I will carry a neutral. Anybody, and Brian, do you guys carry neutral, or anybody where you work? Mr. Beb, 1 second. No? Mr. Beb?
Yeah. I'm wondering, this is the right thing for fixture calculation. I'm wondering, when I was in Solar, we have I was living in a 5-bedroom house, and it has AC units. I'm just comparing with the AC house. The AC units, which is small, not like
Plug in.
here they have a central air.
Plug-in
They're
AC.
plugging.
Okay.
It's those type of, and whenever we come on all this.
Trips.
The
Trips.
whole thing trips and
Yeah.
So it's, normally you have to dedicate a point circuit for each unit of things, or
If you
I
have,
don't know
if you, especially AC units, if a window, they call them window AC units. The window AC units, if it's, there are two rules, if you guys remember that one. If you have window air conditioning that you need to feed, these receptacles are dedicated for, not for window air conditioning, no air conditioning. If you have window air conditioning that you need to plug from these, and you know that, then you have the window air conditioning cannot be more than 50% of the circuit size. So if your circuit is 20, the largest window air conditioning you feed from it is 10 amps. If it's sharing light or receptacle with it. And if it's not sharing light or receptacle, if it's dedicated circuit, dedicated receptacle for it, it's 80%. So that's how we should design it. But we really, well, commercially, definitely commercially, and even residential, what I would suggest, if you have a window air conditioning, pull a 20 amp circuit for that window air conditioning, call it a day. It's not a good idea to share it with other loads. Not a good idea. In residential, you can, because you don't, most of the receptacles sitting there doing nothing really. In a commercial building office, the last thing you want to do is put an air conditioning plugged in the same circuit that feeds all these cubicle receptacles. The last thing you want to do. Not a good idea. But code-wise, you can though, as long as you size it based on 10 amps, no more than 10 amps. Any question, guys? So I thought that will give you at least, as you start circuiting, Spencer, you're going to start moving with the circuits, and always move with, when we circuit, guys, because you're right now, you're going to be doing the power circuiting, always circuit with 3-phase, always in the back of your mind, phase A, phase B, phase C. So 1, 3, 5, or 2, 4, 6, as you start circuiting. So the worst, as you move through, because you can balance the load. So if I want to circuit, if I have 3 circuits in this room and I want to put 3 circuits, you put circuit number 1 here, circuit number 3 here, and circuit number 5 here. I'm guaranteed phase A, phase B, phase C with a common and neutral, good to go. And I move the next room, I go 2, 4, 6, now phase A, phase B, phase C with a neutral, and you keep going. And then you go to the odd, even, and move always in 3-phase, in 3-phase combo. In 3, phase 1, phase 2. Are you guys following with me? As you move, as you circuit, don't just go 1 and 2 and 3 in one area. Always in odds and in 3-phase combo. So you're going to have a 1 and a 3 and a 5 and a 2, 4, 6. So here's the first set of circuits that I'm going to fill. The second set, and then you go to the third set, which will be 7, 9, 11, and this will be 8, 10, 12. Does that make sense? When I fill these, I jump to these, and I go to these, and jump to these, and you keep going in these 3-phase in a system. Light or receptacle. Light or receptacle. In our case, guys, because we have 2 panels, so you really, when you're a receptacle panel, you're going 1, 3, 4, 2, 4, 6, 7, 9, 11, 8, 10, 12, and you keep going. Are you guys getting the rhythm of that circuiting business in a commercial building or industrial? For light or receptacle?
that's multi-wiring.
Multi-wire circuits. You don't ever go 1, 2, 3, 4, 5, 6, 7, 8. You know, because that will get you. You can't go it, but physically, mechanically, guys, you're going to end up with circuit 1 here and circuit 3, 2, all the way down in another room. So put them in the same neutral. It will be, you can, but it will be waste of money. You already moved to a different room. You could drag your neutral all the way to a different room. So, any question guys about lighting and receptacle circuiting? That's exactly what chapter 4 Spencer was talking about. Grouping. Can I group lights? Yes, I can group them. Can I group lighting circuits in one conduit? Yes. Why? Because they're less than, well, based on Chad's rule, they're number 1 or less. Conductors are number 12. I can group them. Is it a good idea to group lighting circuits or receptacle circuit? Absolutely. You always want to do that. You always want to group lighting circuit and receptacle circuit. It's a very good idea to group lighting circuit and receptacle circuits. Yes, sir.
You drew out 3 rows of like 4 lights or something, you can hear 3 phases across all 3 columns or rows, whatever. You'll obviously have whips in between.
Yep.
But how many J boxes will you have down the column?
Yeah.
Will you just have the J boxes at the starting
Well,
points and then moving down, or?
rule of thumb is you don't want more than 5 whips coming out of a J box.
Right.
4 to 5 whips. So you do your math. So if I'm coming here, here's a whip. If I want to put a J box right in here, so feed these. There's 1 whip here, 1 whip here, 1 whip here, 1 whip here, 4. And a conduit coming in, conduit coming out, go to the next, have another J box, 4 whips, and you keep going. Does that make sense?
Yeah.
That, at least that's how I seen it done, or that's how we do it. Now, is it wrong if there's a 5th one to add it? No. No. Brooks, I'm sorry, do you say something?
I was thinking of the daisy chain. You have 1 box.
With K, with where? Yeah, you can do that. Yes. Yeah, if you want to wire with MC cable, just bring your home run cheapest way, bring your home run conduit to first box, take your MC cable and go from the fixture 1, tie it to fixture 2, to fixture 3, to fixture 4. Yes, you can. Yeah, you don't have a limit of how many you can feed because you're feeding fixture. But at the end, though, you can't go feed a receptacle from the same circuit. Remember that rule. You can feed a light, a switch, but if you can keep so J box here, from here whip to here and here, all in the same circuit or different circuits. But as long as it's lighting related circuit, that's a cheaper way of doing it. Other than what the best way really, but remember, you are going to be using your conduits for also the receptacles, not just the lights. That's another thing. If you design your conduit system right, you can utilize the same conduits to pick up your receptacle load and to pick up your lighting loads, and you might be able to pick up some small equipment load. If you have a tiny little motor, 5 horsepower motor, you need to pull these number 10 conductors. You might be able to pull them through the same conduit system. Yeah, you can. I mean, there's a number 8, number 10. I would group number 10. I will put number 10, number 8, number 10 motors. It's the conductors number 8 and especially number 8, number 10, and number 6. 6, 8, 10, not a big deal. Higher than that, you need a dedicated circuit. But you're going to go by the engineer. The engineer said dedicated circuit. You're going to give a dedicated circuit with conduit. Good point. Any question, guys? Any question? Well, I'm going to respect Friday and respect your time, unless you want to hear, because I need probably another half an hour to finish the rest. But I'm going to stop right here, guys. And when we come on Monday, we have a guest speaker. But after the guest speaker leaves on Tuesday, what I'm going to do, I will cover the last 2, which is a chiller. These chillers and motors are really easy because there is no monkeying around with them. So I'll cover the chiller as well as the motor, and then that will cover everything that you need to circuit in the project, I believe. You disagree with me, Mr. Van? Okay. Any question, guys?
Test Wednesday or Tuesday?
I'm not sure. We have 2 speakers next week, so I don't know how our schedule is going to go next week. I really do. We have a speaker. We have Todd Christensen coming on Monday, guys. Really good presentation, I hope. Okay, thank you for listening to Chad. To be continued.